Hello again. So far, we have learned that the expected value is used when trying to predict future events. Sometimes the result of the expected value is confusing or doesn't tell us much. For instance, let us discuss a very famous example, throwing two standard six-sided dice and adding up the numbers on top. We have 6 options for what the result of the first one could be. Regardless of the number we roll, we still have 6 different possibilities for what we can roll on the second die. That gives us a total of 6 times 6 equals 36 different outcomes for the 2 rolls. For clarity, we can write out the results in a 6x6 table, where we write the sum of the 2 dice. You can clearly see that we have repeating entries along the secondary diagonal and all diagonals parallel to it. Notice how 7 occurs 6 times in the table. This means we have 6 favorable outcomes. As we already mentioned, there are 36 possible outcomes, so the chance of getting a 7 equals 6 over 36, or just 1/6. Let's also compute the expected value for this event. Since we are dealing with numerical data, we should apply the same formula we used for the archery problem from the last lecture. To do so, we must assign an appropriate probability to each unique entry in the table. Just like with the sum being 7, we do that based on the number of times the number features in the table. If we do so, we are going to get the expected value, which ends up being 7. But how important is this value if the probability associated with it is only 1/6? The sum being equal to 7 might be the most probable answer, but it is still very unlikely to occur. Thus, we cannot reasonably bet on getting a sum of exactly 7. Moreover, even though we are suggesting 7 is the most probable sum, how can you be sure? What we can do is to create a probability frequency distribution. Simply put, a probability frequency distribution is a collection of the probabilities for each possible outcome. That's how I know that 7 was the most probable sum of 2 dice. Usually, it is expressed with a graph or a table. To understand what a probability frequency distribution looks like, we are going to construct one right now. Using the sample space table we already constructed, for each unique sum, we record the amount of times it features in the table. This value is known as the frequency of the outcome. For example, getting a sum of 8 in 5 different cases means that 8 has a frequency of 5. Okay. If we write out all the outcomes in ascending order and the frequency of each one, we construct a frequency distribution table. By examining this table, we can easily see how the frequency changes with the results. Good job. At this point, we've done most of the work. The final step in getting the probability frequency distribution might be the most intuitive one. We need to transform the frequency of each outcome into a probability. Knowing the size of the sample space, we can determine the true probabilities for each outcome. We simply divide the frequency for each possible outcome by the size of the sample space. A collection of all the probabilities for the various outcomes is called a probability frequency distribution. As mentioned earlier, we can express this probability frequency distribution through a table or a graph. All right. On the graph, we see the probability frequency distribution. The x-axis depicts the different possible numbers of spades we can get, and the y-axis represents the probability of getting each outcome. When making predictions, we generally want our interval to have the highest probability. We can see that the individual outcomes with the highest probability are the ones with the highest bars in the graph. Usually, the highest bars will form around the expected value. Thus, the values around it would also be the values with the highest probability. This suggests that if we want the interval with the highest probability, we should construct it around the expected value. Before we move on to the next section, we need to talk about the opposite of an event. The term we use in probability theory is the complement, and we are going to explain why it is so important in the next lecture. See you all there, and thanks for watching.